Nuclear Chemistry, Part 1. What is the difference between a nuclear and a chemical reaction? In a standard chemical reaction, no new elements are produced. In the reaction, we only involve the electrons. The nucleus of the atom plays very little role in a standard chemical reaction. Only a relatively small amount of energy is absorbed or released in a chemical reaction on the order of maybe 800 kilojoules. The reaction rate for a chemical reaction depends upon external factors like temperature, the presence or absence of a catalyst, the concentration of the reactants, pressure conditions, and other factors. In a nuclear reaction, elements can be interconverted, producing new elements, or converting one element into another element. In a nuclear reaction, the particles of the nucleus are directly involved in the reaction. A large amount of energy is absorbed or released in the order of tens of thousands of kilojoules in a nuclear reaction versus a chemical reaction. And the rate of the reaction is controlled internally, so external factors like temperature and pressure don't really play a role in a nuclear reaction like they do in a chemical reaction. And the history of nuclear chemistry starts in the mid to late 1800s, the 19th century. In 1896, Henry Becquerel discovered what he called uric rays. Crystals of uranium were found to glow, and when he placed these uranium crystals in a dark room, they still continued to emit some sort of light from them, despite the absence of light that would enable a phosphorescent or fluorescent compound to be able to absorb and release that light. This phenomenon was explored by Ernest Rutherford, and he came to the conclusion that the uric rays came from the uranium itself, that the crystals were actually emitting a light that they produced on their own. He further determined that this light came from the spontaneous disintegration of the nucleus of the uranium atoms in the crystals. Marie Curie and her husband Pierre did further work into radioactivity and radiation. Their work coined the term radioactivity, which would have previously been called this uric rays, that was found to be a type of radioactivity. And she was responsible for the discovery of a number of different radioactive nuclides. Nuclides refers to different nuclei in an atom. So a helium atom versus a carbon atom, for instance, would be two different nuclides, whereas the term isotope refers to differences in the nucleus between atoms that are of the same element. A nuclide refers to different atoms, period, whether or not they are of the same element. Now, radioactivity is emission of particles from the nucleus of an atom. They are emitted from the nucleus rather than being phosphorescence, which is the release of light from electrons. So in a radioactive particle, you actually get something coming out of the nucleus rather than light or something being emitted from electrons. There are several different types of emissions. You have positrons, you have alpha particles, beta particles, gamma rays are all types of radioactive emissions. And when we talk about radioactivity, we typically use chemical symbols with the format A sub Z and X. X represents the elemental symbol, A the mass number, and Z the atomic number. So looking at the symbols for the various radioactive particles, positrons have the symbol E with a superscript of 0 and a subscript of +1. This denotes that they have no mass and a positive charge. Alpha particles have the symbol alpha with a superscript of 4 and a subscript of 2. This denotes that they have a mass of 4 and a charge of 2. Beta particles have a superscript of 0 and a subscript of -1. This indicates that while they have no mass, they have a -1 charge. A beta particle is essentially an electron, whereas a positron is a positive electron. An alpha particle is essentially the nucleus of a helium atom that has had its electrons stripped off. Lastly, we have gamma particles, where gamma particles are simply energy. They're the lowest end of the electromagnetic spectrum and has no mass nor charge and is represented with the symbol gamma. Decay equations are chemical equations that we write in order to represent a nuclear process. So rather than a chemical reaction, it's a nuclear reaction. When writing a decay equation, we write the parent nuclide on the left and the daughter nuclide or nuclides on the right. There are two rules in writing decay equations. One is that the sum of the mass numbers must be equal. This means that mass is conserved throughout the decay process. The second is the sum of the atomic numbers must be conserved. They must be equal, which means that the charge is balanced. If I look at an example here, the decay of polonium to lead, we have 210 in polonium as its mass number going to lead 206. The difference between 210 and 206 is 4. The atomic number of polonium is 84. The atomic number of lead is 82. The difference is 2. We have a mass difference of 4 and an atomic number difference of 2, which is the amount that is in an alpha particle. So if I look at the right-hand side, the lead atom and the alpha particle added together equal the left-hand side. Now, alpha particles are particles that are emitted primarily by compounds that exist at bismuth and above, so element number 83 and higher. All the nuclei above bismuth are inherently unstable, and thus they're radioactive. Their nuclei spontaneously fall apart. If I look at the alpha particle then, it's the emission of a helium doubly charged nucleus, 2 protons and 2 neutrons. We see that the nucleus will emit that particle, and this is what causes alpha decay. An example of this is the decay of radium to radon. 226 to 222, we have a difference between mass numbers of 4, 88 to 86, a difference of atomic number of 2. The decay of an alpha particle is spontaneous. Those atoms that are at uranium and above uranium will actually undergo a fission process because they're even heavier and their nuclei are even more unstable. But with the ones that are between 83 and the 92 that is uranium, we'll see a spontaneous alpha decay occur. The radiation from an alpha particle is the highest ionizing. That means it has the greatest ability to actually cause damage, but it is the lowest penetrating, which means it's the easiest to stop. A beta particle emission is a process by which we have a process where there are too many neutrons and not enough protons. So during the course of a beta particle emission, we have a neutron being turned into a proton, and it releases a beta particle, which is more or less an electron. So if we look at the overall decay process for this, we're taking a neutron with a mass of 1 and a charge of 0 and converting it to a proton with a mass of 1 and a charge of 1. The release of this is accompanied by the release of a beta particle with a mass of 0 and a charge of negative 1. And we can add the 1 and the 0 on the right-hand side, and that will give us the 1 on the neutron. Adding the negative 1 and the positive 1 on the right-hand side gives us a 0 on the left-hand side, so we maintain our balance properly. So if you look at what's going on with this, we have, for instance, a carbon nucleus being converted to a nitrogen nucleus where we're releasing the beta particle, which is essentially the electron. Another example is the decay of radium-228 to actinium-228, where we see the release of a beta particle here. If we add 228 and 0 on the right-hand side, we get the 228 of the radium. And if we add 89 and negative 1, we get the 88 of the radium. Now the radiation of a beta particle is intermediate in its ionizing power and intermediate in its penetrating power. So it's moderate in its ability to do damage and moderate in its ability to get through. Positron emission, on the flip side, is a case where we have too many protons and not enough neutrons. So in the case of positron emission, we have the release of a proton becoming a neutron and releasing a positron, which is essentially a positive electron. And in this process, we take a proton with a mass of 1 and a charge of 1 and convert it to a neutron with a mass of 1 and a charge of 0, releasing a positron with a mass of 0 and a charge of 1. Now we see with this positron symbol, as with the beta symbol that we saw a minute ago, that we can write this beta symbol in addition to writing the little e that we saw in the lineup of the different particles. So either writing the beta symbol or the little e for a positron or a beta particle is acceptable. Either one you can use interconvertibly. So in this kind of process, we have a conversion of a proton to a neutron releasing a positron. For example, potassium-38 can decay to argon-38. If we add 38 and 0 on top on the right-hand side, we get the 38 for the potassium on the left. Adding 18 and positive 1 on the bottom of the right-hand side gives us 19 on the left. And the radiation for positron is analogous to that of a beta particle, where we have intermediate ionizing and intermediate penetrating power. Now, gamma rays are electromagnetic radiation rather than actual physical particles. They don't have a charge or a mass, and they release radiation in addition to things like decay processes, for example, the decay of uranium-238, uranium-235, cobalt-60, things like this can all release gamma rays, where gamma rays are electromagnetic radiation on the order of 1 × 10⁻16 meters on the low end of the spectrum. So the radiation for a gamma ray is the lowest ionizing and the highest penetrating, which makes it the most difficult to stop and therefore one of the more dangerous particles. An example of this, something that's used in radiative therapy, is the decay process of cobalt-60, which decays by beta decay. Cobalt-60 is transformed into nickel-60 with the release of a beta particle and an accompanying gamma radiation as well. So in summary of the radiative process then, we have the alpha particle, which is a decay of essentially a helium nucleus being released. It is the highest ionizing but the lowest penetrating power. The beta emission is the emission of a conversion from a neutron to a proton, releasing essentially an electron. It has moderate ionizing and moderate penetrating power. The positron emission at the bottom is also moderate in both its ionizing and penetrating power, and is the conversion of a proton to a neutron, releasing a positron. In the middle, the gamma radiation releases a photon of gamma ray that is in the order of 1 × 10⁻16 meters in its wavelength, and has low ionizing but high penetrating power. So how does one detect radiation? There are a number of ways. Photographic detection is one way, and just like with a light source, a photographic plate can be exposed to a radiation source, and that exposure will cause it to strike the plate, and that can be developed, but it's difficult to quantify. Measuring fluorescence is a second method. If we expose radiative sources to a fluorescent material, it will cause fluorescence in that matter. The release of the energy can be measured by a scintillation counter to quantify the radiation. The cloud chamber is a third means. A cloud chamber is a vapor-filled chamber which, upon exposure to radiation, causes particles to ionize. If we condense that vapor down, it cools into a liquid, and it will condense around the ion, and you can see traces of that in the cloud chamber. The most common means of detection is what's called a gas ionization or Geiger counter. This operates with the radiation entering through a variable slit in the Geiger counter, which will ionize argon. The ionization of the argon produces positive argon atoms and electrons. The positive argon atoms will move to the negative cathode. The negative electrons will move to the positive anode. This completes the circuit and causes emission of a sound. If I look at the counter, it looks kind of like this. Connect to a battery, you have a detector connecting to it, and when the circuit's completed, you get a noise, like a clicking noise, out of the counter, which is what you hear in the movies where people are walking around with the funny little meters making the clicking sound.